Hi, this presentation is about radians and degrees, and the first thing we're going to start talking about is angles. So any angle is composed of two rays with a common endpoint, and that endpoint is called the vertex. One side is the initial side, and the other side is the terminal side. If you just got an angle hanging out there, it doesn't really matter which one's initial or which one's terminal. But we usually put angles in what we call standard position, where we put the initial side on the positive x-axis, right along here. If we go from the initial side to the terminal side in a counterclockwise direction, like that, then we say the angle has a positive measure. If we go in a clockwise direction, then the angle has a negative measure. And it's common convention that when we're talking about angles, we usually use Greek letters. For example, we might call this letter alpha. We might call this angle beta. You'll also see the letter theta used to represent angles a lot. Okay, so how do we measure angles? Just like we measure distance in different units, feet, meters, miles, we measure angles in different units. The most common measure you're familiar with up to this point has probably been degrees, where we split a circle up into 360 tiny little divisions. So we start at 0, quarter of the way around is 90, halfway around is 180, 3/4 of the way around is 270, and then all the way around the circle is 360. Another way to measure a circle, and it's just a different unit of measurement, is something called radians. And it's derived from the formula for the circumference of a circle, which says that that is equal to 2 pi times the radius. Well, when we're measuring angles, it doesn't matter how big the radius is. So if we just make the radius equal to 1, then all the way around the circle is 2 pi, which is about 6.28. That means that 1 radian is, well, let's think about it this way. 0 radians is right here. Halfway around is pi radians. So that means that pi radians equals 180 degrees. And that little fact is going to be our conversion factor. So if I want to start here and go all around the circle, it takes me about 6.28 radians to do that. Put that 0.2. That looks better, doesn't it? Okay, so let's do some converting. What is 30 degrees in radians? So I'm starting out with 30 degrees. I want to end up with radians. This is just like unit cancellation in chemistry. So I have pi radians over 180 degrees. 30 goes into 180 6 times. So 30 degrees is equal to pi over 6 radians. And we don't usually write radians. We just assume what they are. How many degrees are 5 pi over 4 radians? Okay, this time I'm starting with radians. And I'm going to multiply by 180 degrees over pi radians. So the pi's cancel. And 5 times 180 over 4 is 225 degrees. You can also do that on your calculator. What you need to make sure is that you are in radian mode right here. And if I want to convert 30 degrees to radians, I go 30, then second angle, and hit 1, hit enter, and that's how many radians it is. If I want to go to from degrees from radians to degrees, I can go 5 pi over 4 second angle hit degrees 225 degrees. Most of the time, though, the conversions are easy enough that we can just do it in our head. Later on, we'll talk about which angles you need to have memorized in terms of degrees and in radians. If we're measuring things in degrees, we can also knock those degrees down into smaller units. For example, 1 degree is equal to 60 minutes. 1 minute is equal to, guess what? 60 seconds. So if I want to convert 38 degrees, 48 minutes, and 27 seconds to decimal degrees, I'm going to take the 27-minute part, and that's a fraction of 27-second part. That's a fraction of the minutes. It's actually 27/60ths of a minute. I'm going to add that to the minutes I already have, in this case 48, and that's how many minutes. Then I'm going to divide the minutes by 60 to convert them to degrees and add them to how many degrees we have, in this case 38. So 38 degrees, 48 minutes, 27 seconds is equal to 38, whoops, is equal to 38.8075 degrees. If I were going from decimal degrees to degrees, minutes, seconds, I would take the decimal piece, this right here, I would multiply it by 60, and that would convert it to minutes. Then I'd take the decimal piece of that, multiply that by 60, and that would convert it to seconds. Okay, arc length. Arc length is really easy to work with as long as we are working with radians. The arc length, the distance that it takes to travel from this point down here to this point up here, is equal to the radius times the central angle. But theta must be in radians for this to work. Okay? If you're in degrees, you've got to convert by multiplying by pi over 180. For example, find the length of the arc on a circle of radius r intercepted by a central angle theta. In this case, r is 9 and the angle theta is 60. So there's r. That's 60, and we want to measure this arc length right here. Well, S is going to equal 9 feet times 60, and I'm going to convert that to radians, and that ends up being 9 times pi over 3, which ends up giving us 3 pi feet, or about 10 feet. So if I travel 60 degrees along this 9-foot 9-foot or 18-foot diameter circle, then I will have traveled about 10 feet. We can use this with maps. The radius of the Earth is about 4,000 miles. Here's the equator, that's 0. Dallas, Texas, that angle right there is about 32 degrees, 47 minutes. And this angle up here, exaggerated of course, is Omaha. And that's 41 degrees, 15 minutes, 31 seconds. Okay, so we need to convert everything to decimal degrees. I'm going to go 31 divided by 60 plus 15. Divide that by 60 plus 41. And that is 41. Let me get my calculator back. That is 41.259 degrees. 32 degrees 47 seconds is 47 divided by 60 plus 32. That's 32.783. 32.783. So now I'm going to go 41.259 minus 32.783, 8.476. That's our central angle. I'm going to convert that to radians by multiplying by pi over 180. Multiply that by the radius of the Earth, and they're about 591 miles apart. Let me grab all those calculations for you. And we'll put them in the notes here. Okay, last thing we need to talk about is linear speed versus angular speed. Linear speed is how much you travel along the circle over the time it takes to do that traveling. Angular speed is how much of an angle you travel divided by the time you're spinning around. The difference between the two is best illustrated when you think about the George Washington celebration and the soldiers are marching around in circles, and to keep the same angular speed, this poor girl that's out on the outside has to walk a lot farther than the ones near the center. So she has to really run to keep up with the ones that are going around in the center. So the linear speed increases as you increase your radius. Okay, we've got one more problem to work through, and we're given that compact disks spin at a constant linear speed of 1.3 meters per second. So we can say 1.3 meters per second is equal to our arc length over time. We'll just use 1 second for convenience sake. We want to figure out what the angular speed of a point on the CD 5.6 centimeters from the center of the disk is. So that's going to be our radius. Notice that that's in centimeters, so we'll convert that to meters to keep everything consistent. Okay, so S equals 1.3. That means that we need to convert that. Remember that S equals r theta. We need to convert that to a central angle. So S equals r theta. That means 1.3 divided by 0.056 will equal our theta. And let me get my calculator back. There we go. So 1.3 divided by 0.056 gives us 23.21, and that'll be radians per second. So theta is equal to 23 point, what did we say that was? 21. Okay, 23.21. And our angular speed then, which is written as omega, funny looking W, is our central angle, 23.21, over our time, which we said we're going to set at 1 second. And that's the angular speed.